Okay, for part C, now we want to move on. We want to find the change in kinetic energy of the block. So we are doing some work, right, by pulling this block down. So let's figure out what that is. So we know that work, right, would be equal to our change in kinetic energy. So we basically solve for all of the pieces that we need for kinetic energy because we know that our general expression for rotational kinetic energy is going to be equal to 1/2 m r, sorry, 1/2 m, I'm getting ahead of myself, w squared. And because we're treating it as a point mass in this case, just in this case for this problem, we know that our KER is going to be equal to 1/2, and then we're going to plug in our I, right? Because we used I for point mass. So we just had mr squared. So mr squared, right? Times w squared. Okay. So we're going to take our initial kinetic energy and then our final kinetic energy, and we're going to figure out the change in between those, and that's going to give us the work that we did by pulling that block down, right? Because we applied a force, we moved it down, and that's the work that we did. Okay, so work is equal to our final, right? KF minus, sorry, uh, I'm changing the subscript, but these are also rotational. So this R over here just means rotational, right? Which is rotational kinetic energy. I'm just specifying like what kind I have. F means what my final, right? And then I means my initial, but they're both still rotational kinetic energies, right? The subscripts are trying to try to help specify some things, but I'm sorry if they end up being confusing to some people. I just want to clarify what I mean. Okay, so what is the final? So this is our general expression, right, for the rotational. So what's the final one? So our final would be 1/2 mb, mass of the block, right, times the initial radius squared, right, times the initial angular velocity squared, right? And then, oh, I'm sorry, this is this is everything initial. That's backwards, right? Because I wrote final. This would be my final, this would be my initial. So we're going to subtract the initial, right? Because I want to know the change, right? So where I'm at minus where I started is going to be the change. Okay. So let's see where I'm at the end. Where I'm at the end would be this. So 1/2 mb, and then we have rf, right? Squared times wf. Okay. All right. So looking back at what we found, so we have all of these things, right? We have the mass of the block. We were given that by the problem. So we have that. We also have our final radius. We have our initial radius. And we found WF from the previous problem. So we have this WF and we have this WI, right? So we have everything. We have this guy and we have this guy. So let's just go ahead and assume that we've plugged everything in. And we solved our math here. So the change in kinetic energy, so our delta KE, right, is going to be equal to 0.1, sorry, 0.3 joules. Okay, so that's going to be our change. All right, so good. So, all right. So yes, so to summarize, yes, the angular momentum is conserved. What's our new angular speed? We found it over here by using conservation of momentum. We found it says what's the change in kinetic energy, right? And then how much work was done in pulling the cord. So we found our change in kinetic energy, and we know that that's also the same for C, right? So the answer for C is also that our change in kinetic energy is equal to our work from pulling the cord. Okay. So hopefully that one makes sense. Because you're not here to ask me questions. So yeah, leave something in the comments if you feel like there's something else that you want clarification for, and I will see them and respond to them in a timely manner.